Great. Okay, let's get started. Good afternoon. Let's continue our discussions. So yeah, now this talk will be about multi-pitch analysis or pitch analysis. I have like 70 slides, so I'll try to move quickly so that I can finish in time. This is a brief outline. We are gonna first talk about the basic concept of pitch, and then we will briefly review single pitch detection. I think that's a great learning material for people to start working on pitch analysis problems. And then we will have a categorization of multi-pitch analysis problem setups and briefly review several methods. So pitch, according to ANSI, is defined as an attribute of auditory sensation. So it's a subjective perceptual attribute, in terms of which sounds may be ordered on a scale extending from low to high. And it further explains that it depends mainly on the frequency content of the stimulus, but also depends on the sound pressure and the waveform. And the operational definition is that we define the pitch of a sound by matching its height to a reference tone. The reference tone is a sine tone of a given frequency at 40 dB SPL. Okay. But pitch actually has relation with intensity of the sound as well. For pitch of low frequency, say below 1000 Hertz sine tones, if you increase the intensity of the signal, the pitch perception actually would decrease. That means low loud sounds go flat. But for high frequency tones, say over 3000 Hertz, when you increase the intensity of the tone, the pitch tends to go sharp. Okay, let's have a quick feel of this. That's loud, but do you feel when the intensity increases, it go flat? And this is a high tone. Okay. I don't want to make it too loud. But for high frequencies, when I increase the intensity, it tends to go sharp. For harmonic sounds, we can define the pitch more reliably. So a harmonic sound is defined as a sound with strong sinusoidal components at integer multiples of a fundamental frequency. And these components are called harmonics or overtones. And for this type of sounds, the pitch percept is reliable, across different people and across different times for the same people. So for this type of sound, pitch is well defined, we can say. And here's some sounds are harmonic, right? Strongly harmonic. For example, a sine wave only contains a single frequency and it's harmonic. Now there are other musical instrumental sounds like an oboe sound or clarinet sound. When we listen to it, we can clearly match the height to a sine wave. Okay, so the pitch is perception reliable. And when we look at the waveform of these notes, we can see periodic patterns in the time domain and clear harmonic frequencies in the spectral domain. The waveform of different musical notes of different instruments, they are of different shapes, but their periods are the same if their pitches are the same. And also their spectral shapes, distribution of energy is different across the different instruments. And that's related to time. But pitch is only about where the peaks are. Right? From that, we can find out the fundamental frequency. Some musical notes are just quasi-harmonic or somewhat harmonic. For example, this marimba note. For these kind of notes, often we can also match them reliably to a pitch percept. But when we look at the waveform, it's not that periodic anymore. For example, the amplitude decreases. And when we look at the spectrum, it's not that harmonic. Some strong peaks happen at non-integer multiples of the fundamental frequency. And human voice is also could be quasi-harmonic during the speech utterances. Right. Because the vowel has changed within this short period of time during speaking. So, and the pitch also has changed a little bit. When we look at the waveform, it's somewhat periodic, but the shape is not exactly the same from the first period to the last one. And when we look at the spectrum, it's the harmonic patterns are not that clear either. That's mainly because during speech, the vowels and pitch constantly change. Whatever short period you take for analysis, the pitch content might has already changed. But during the analysis of this short frame, you're not taking the sequential information, right? You're basically displaying all the frequency content in the magnitude spectrum. So it doesn't tell us what frequency happens at what time within this frame. Now, some other notes are inharmonic. For example, this gong instrument is a percussive instrument. If I ask you what pitch you perceive, different people will give us different answers. And if you listen to it several times, your answers may be different too. So for Western musical instruments, this is a categorization. You know, these woodwind, brass, echo string, and pluck string, and vocal, they are harmonic. These are corresponding instruments. And pitched percussive instruments are considered quasi-harmonic, like timpani and marimba and so on. And non-pitched percussive instruments are inharmonic. This is a table copied from Nancy Cloughery's edited book on signal processing methods for music transcription. So let's come back to the first principles. If we are trying to design an algorithm to detect pitch from signals, we need to first understand what aspects of the signal would be correlated to pitch, right? So let's take a think about it. We're dealing with, you know, a complex tone. Complex tone means there are more than a single frequency. A sinusoid will be a simple tone, but a harmonic sound, you know, containing multiple harmonic frequencies will be considered complex tone. So when we look at a complex tone, what would be related? What is related to pitch, right? Would that be the strongest frequency component? Would that be the lowest frequency? Would that be something else, right? Let's listen and explore. So maybe one hypothesis is that pitch is determined by the lowest strong frequency component in a complex tone, right? From this example, it's reasonable. When we look at the spectrum, the lowest strong frequency component is this peak, and its frequency is 259.7 hertz. And when we listen to the tone, and if you have a sine wave generator that you can change the frequency of the sine wave and try to match these two sounds pitch, you will see that your matched frequency of the sine wave is very close to this 259.7 hertz. Right, so this hypothesis applies to this example. But there's a phenomenon called the missing fundamental phenomenon. So here we will listen to 5 complex tones. The first complex tone has 10 strong frequencies. They are equally spaced in frequency. And the second one does not have the first frequency component. The first one is considered fundamental frequency, right? And it only contains the second, third, and so on to the 10th harmonic. And the third one misses the fundamental and also the second harmonic, and so on. So let's listen to it and try to feel whether you think the pitch has changed or how much is the change. What do you think? Do you think the pitch has changed? No change. No change. What has changed if the pitch is not changing? Timer is changed. That's right. Yeah. So this is an excellent example to invalidate our previous hypothesis, because starting from the second complex tone, the first strong frequency does not equal to the pitch we hear. Okay. So we need to come up with a different hypothesis. How to generate? So you can just add multiple sine waves together.
So fundamentally is not there. Only like square wave and then
no, so you can
the harmonics like that.
So you can do, you know, you can generate a sine wave for this frequency, another sine wave for this frequency,
okay,
and then add them together.
Okay.
Yes. Okay, so let's come up with another hypothesis, but maybe multiple hypotheses, right? Maybe it depends on the loudest frequency in the signal. Maybe it also depends on the common frequency that can divide the other frequencies, other strong frequencies. Or maybe it depends on the space between the regularly spaced frequencies. Okay. For example, here I made this example. It's a weird example. You don't find it in nature. But this complex tone contains a 300 Hertz component, a 500 Hertz component, and so on. The space in between is 200 Hertz. The first component is at 300 Hertz. The common divisor, the greatest common divisor of all the frequencies is 100 Hertz. So if we listen to it, do we hear 100 Hertz or 200 Hertz or 300 Hertz as a pitch? Right, that's a question. Let's listen to it. What pitch do you hear? Do you hear single pitch? And if it's a single pitch, what can you hum it? Or do you hear two pitches? Let's listen to it again. One pitch. What's a pitch? 200 Hertz. Who'll hear this? Let's listen to the 200 tone. Okay, and 300 Hertz tone. Let's listen to the complex tone again. Yeah. Well, so it's a complicated example, right? But in this case, the pitch is not really definite. You know, some people may hear 300, some people may hear 200, some people may hear 100. I don't know. But in nature, we do not have this. This doesn't follow physics. I mean, you would have to miss so many harmonics to get this sound, right? Okay, so this is just to illustrate that pitch concept can be quite complex, but we are in engineering or in pitch detection research, we are focusing on harmonic sounds. For harmonic sounds, we don't have these kind of complications. And pitch can be reliably mapped to the fundamental frequency. And the fundamental frequency would correspond to the regular space between adjacent harmonics most of the time, and also would correspond to the greatest common divisor of all the harmonic components. Okay. So we don't have that complicated issue. So again, pitch is a perceptual attribute. It's subjective. It differs from one person to another and from one time to another for the same person. And it's only defined for quasi or harmonic sounds. And it can be reliably matched to fundamental frequency for those quasi-harmonic sound and harmonic sounds. So in computer audition or IMIR, people do not generally discriminate between pitch and fundamental frequency. We view them as the same thing because we're only discussing harmonic sound in this context. And F0 is the physical attribute, so it's objective. A signal, if it has a fundamental frequency, then it's definite. So now let's briefly talk about the relation between pitch and music. Right? Pitch is very common in music, but there are several questions like how do we tune pitch in music? If you compose music, what set of pitches do you use if you use quantized pitches? And how do we represent pitch in music? If you need to notate them down, how do you represent them? And also, how do we represent the relation of pitches in music? What's the interval? Right? So Professor Rao yesterday already presented the tuning, equal temperament tuning, and also just intonation tuning. So just a brief review. Equal temperament tuning is to divide an octave. An octave is a relation of 2, or power of 2, right? In terms of the frequency in hertz. We equally divide one octave into 12 half steps in the logarithmic scale. And we can, using mathematics, we can write it down as this. So we start from the reference fundamental frequency or frequency F. And if we want to move n steps above higher, we multiply this with this quantity. Okay. For example, if we want to move 12 steps higher, which is 1 octave higher, then this is 2. So we double the reference frequency to arrive at 1 octave higher. If we move just 1 step higher, which is a semitone, then this is 2 to the 1/12th power, which is about 1.059, something like that. And 1 step is a semitone is still too wide for music representation. So in music, people further divide 1 step, or one semitone into 100 cents. So a semitone is also called a half step. In music terminology is kind of weird, but a semitone is a half step. A tone is a step. So that's but we further divide a half step into 100 cents, also following the logarithmic frequency scale. And 2 half steps makes a whole step. 12 half steps make an octave. So if we use this cents as a unit, then we can, calculate the difference between the frequency f and the reference frequency using this formula. So we replace 12 with 1200 here. So 1 octave will contain 1200 cents. For equal temperament tuning, we also need a reference note, right? Here, we only define the relation between notes, between pitches, but we need to define this reference pitch. So nowadays in Western music, people use A as the reference pitch, and people define A to 440 hertz, or maybe 441, 442 hertz. But say 440 is a very common reference. So once you define A, then you can define other pitches, say B, right, C, and so on. Define all those half steps or every note in the octave. Okay, so on the piano keyboard, right, this is A, is 440. Then A sharp is 1 half step above. It's 466. And B would be a whole step above, so 493. And if we go to the higher octave, okay, then that's 880 hertz. You can also go down to compute other frequencies. In music terms, we call these different intervals with different names. If our reference pitch is C, and if you look at the relation between the reference pitch C and another pitch, for example, C and C itself is called a unison. C and C sharp is called a semitone relation, right, or a half step relation. C and D is a major second relation, or a whole step, whole tone relation, C and D. Now C to D sharp is a minor third relation. C to E is a major third. C to F is perfect fourth. No, it's called perfect fourth, and we'll see why it's called perfect. And C to F sharp is called tritone. C to G is called perfect fifth, and we will see why it's called perfect again later, and so on. Okay, so there are musical terms to describe the relations between pitches. And in music notation, in Western staff notation, we use 5 lines, to notate notes. And this is a treble clef. So this last second line is a G, because this symbol looks like a G, right? It's a G, letter G. And this line, the second line here from the bottom is G. And this note, 1 line below the 5 lines is C. So here we have a C and also a D flat. We can also call it a C sharp, or so in MIDI they are equivalent, but in notation this is D flat. And this is a minor second relation or half step relation. But we have other relations too. So here we have a C and another high octave C. That's an octave relation. Yeah, so that's how musicians notate the relations between notes. And then now let's do some computation. So we know the equal temperament tuning, and then we can compute the frequency difference or frequency ratios between different pitches. Right? Say, if we move from lower C to a higher C, we know that it's 12 half steps, and 2 to the power of 12 over 12 is 2 to 1. So the frequency doubles. If we move from C to G, we know that there are 7 half steps. If you count from this C to this G, you hop 7 times, so 7 half steps. And this quantity is 1.4983, very close to 322. Okay. And if we move from C to F, there are 5 half steps, and this quantity is very close to 423. And if you move from C to E, That's 4 half steps, and its quantity is kind of close to 5 to 4. Okay, so they are close to these small integer ratios. And this is not a coincidence. It's based on physics of vibration. For example, if we are trying to vibrate a string, right? Say a string has a fixed length. They are fixed to these two ends, and the string vibrates. Now, if you watch the vibration of the string, okay, there are a bunch of standing waves. Now, the vibration contains many modes, and there's a fundamental vibration where the this wavelength is twice of the length of the string. Okay, that's a fundamental, corresponding to the fundamental frequency. You also have other modes. This one is the second harmonic. The wavelength is the same as the length of the string. But you also have the third harmonic, the fourth harmonic. You can see that when you vibrate the string, it naturally contains those harmonics. Okay. And when you have two notes, each note has its own harmonics, right? So when the two notes, when their frequencies are having small integer ratios, then many of the harmonics across these two notes will overlap together. They're at exactly the same location. And that causes harmonious feeling. If their frequencies are a little bit apart from the small integer ratio, then many of the harmonics from one note will be slightly off from the harmonic position of the other one. They are not far enough, but they are not exactly the same position either, and that's cause the beating, and both the frequencies will fall into the so-called critical band of hearing. So we remember in the hearing, the auditory sensation talk, I briefly talked about the neural responses of the hair cell and their neural fiber responses to different frequencies. They do not only respond to a single frequency, they actually respond to neighboring frequencies as well. And also we talk about the masking effect. So when a strong frequency is present, it will mask the perception of neighboring frequencies. Now when we have two neighboring frequencies, they are close, they are falling into the so-called critical band, that causes a disturbing effect. So it's not harmonious. And in classical music across the world, people try to make music harmonic, right? That gives people a peaceful feeling. So that's why people design those pitch relations to form the small integer ratio. Okay. So now you can see if we use equal temperament tuning, they are close to small integer ratio, but not exact. Right? So another thought is, why don't we just directly create pitch relations using small integer ratios? Right? And that's a just intonation that Pretty presented yesterday. But another one that's related to that is the Pythagorean tuning. Here we only use this 3-to-2 relation to create pitch relations. We start from the reference tone C. We create another frequency, which is 1.5 times of this C frequency. And then we end up at G. We call it G. It's a perfect fifth relation. Then we multiply 1.5 again, we end up at another pitch. We call it D. That's another perfect fifth. If you keep doing this for 12 times, you will actually go to another C fairly closely. Okay. So this is a so-called circle fifth. If you move by a perfect fifth, you start from C, you can go to G, D, A, E, okay, B, and so on. If you move down, you can first go to F, then B flat, E flat, and so on. So after 12 times either direction, you will go back to another octave of C. Okay. Let's make a calculation. We know that one octave relation is 2 times the reference frequency. A perfect fifth is 3/2, or 1.5 times the reference frequency. If we keep going up by a perfect fifth, right, by 12 times, then we have 3/2 to the 12th power. That is 129.75, which is very close to 2 to the 7th power, which is a 7th octave relation, 7 octave relation, right? But there's some discrepancy. This is not small. This is more than 1%, right? So the difference is 1.75. 1.75 over 128 is more than 1%, which is noticeable, very noticeable. We remember the frequency difference limit is 0.2%. Now this 1% is very noticeable. So this actually makes it not convenient for key changes, because if you always follow the perfect fifths, then when you change the key, you have to have another set of this perfect fifth relation, and they do not map with the previous one you choose. The same applies to just intonation. In just intonation, you're not only using this perfect fifth relation, you're also using other small integer relations to define certain intervals. But when you change the key, the positions also change, slightly change. So it's quite hard to make music with different keys, changing with key changes. And that's why people later use the equal temperament tuning to make key changes easier and also make different instruments work easier to each other together. The key idea is to distribute this kind of error, the mismatch, to every note in the octave. Yes? 3 to 2 has approximation?
So not exactly 3 by 2. You can make the actual 5 by 2 to the power of 5 by 2.
Yes, there is a slight difference. Yeah, exactly.
10 to the power of 5 by 2 and 4 of this.
Pardon? Can you say that again?
Take the power of 5 by 2. And do all this.
Yeah.
Okay, that.
Okay, but first of all, 2 to the 5 over 12 is 1.4983. It's not a small integer ratio exactly.
Take that rational number 2 to the power 5 by 2. 7 by 2. Oh, you're taking
Yeah, 7 by 12. 2 to the 7 by 12.
Taking G.
Yeah, G. So it's a perfect fifth. This is called fifths, but it's a 7 half steps.
Okay. So if you take 2 to the power of 7 by 12 and do the everything.
Yes. It will be close, but still not exact to an octave relation.
I see.
Yeah.
I don't know. One has to do.
Yeah. Right. Yeah. So the key idea of equal temperament tuning is to distribute error into every note, so that when you move by a semitone or a perfect fourth or perfect fifth, they're not exactly perfect. They're not really small integer ratios, but the error is so small that you can basically ignore. Okay, but it makes the key transposition and to make it much easier, and also makes different instruments working together much easier. Okay, let's move on. So and also overtone series. Remember that each note not only contains its fundamental frequency, but it contains the harmonics. If we notate the frequency of the harmonics onto the music staff, we can actually see that they correspond to different note names. Say the fundamental frequency is, for example, is this C. The second harmonic will be 1 octave higher. It's still a C. But the third harmonic is 3 times the fundamental. So there's a 3 to 2 relation. So we actually move from C to G. Okay, then fourth one is a C, because it's 4 times of the fundamental. The fifth one is 5 times of the fundamental, which is 5 over 4 of this note. So it's an E here, and so on. So the overtones actually contain many different notes. Okay, and then if you compute the chroma vector for this note from the spectrum, you will not only see the C pitch class activated in that chroma vector, you will also see the G pitch class slightly activated, the E slightly activated, the B flat slightly activated, and so on. Okay. All right, so that's some basic review of the relation between pitch and the music. Any questions? Okay, I want to say that this is, the Western music theory. For world music, for example, in Indian traditional music, probably this doesn't apply, right? And Indian music has its own tuning systems. Every culture has their own tuning systems, and here we only talk about 3 tuning systems. Yes, question.
So here, in this thing, the just intonation is used, right? This one.
Sorry.
In this one, just intonation is used, right?
Oh, this one is just to show the overtones or harmonics of a complex of a note, where do they fall into the music notation?
And so like if we try to fit these harmonics into one octave, then we'll get the just intonation, right? That is what we are using in Indian music also.
So this one is not about tuning. This one is just to display where the harmonics are on the music staff.
So
Yeah.
my one more question would be, why then, like, if we are going till 12 harmonics, then why aren't we getting all the notes of the octave? See, we'll be missing some sharps and flat if I can see, right?
Which one are you referring to? Is that the so-called fifth part or?
No, in the one which is on the slide.
Oh, this one.
Yeah.
We don't have all the notes. I mean,
Right.
they just happen to be at C or G and E. Yeah.
Okay, so by doing this, we are not trying to get all the notes on the octave.
No, we're not trying to. This is just to show what frequency content a note has.
Okay.
Yeah, naturally it has components corresponding to G, corresponding to the E and B flat and so on.
Okay. All right.
Yeah. For example, it doesn't contain C sharp.
Yeah.
Or not yet. Maybe in the later higher harmonics somewhere, maybe it corresponds to C sharp. But,
All right.
no. Okay. Then shall we move on? Okay, so let's move on to single pitch detection. And I think this is good material to get people on board to pitch detection research. So pitch detection is very important because harmonic sounds are ubiquitous in music, in speech, and in animal sounds. And pitch is an important attribute of harmonic sounds. It relates to other properties. For example, if we are able to detect pitch of music, then we can get the melody of the music. From melody, we can infer the key, the scale, the style, the emotion of the piece. And in speech, intonation is an important aspect. It's useful for word disambiguation for tonal languages. Right? For example, in Chinese, the same pronunciation with different intonation can mean very different things. This is ma is constant pitch, ma is rising pitch, ma. So first down and then up, and ma, that's going down. So they can mean very different meanings. And we know that intonation is also important for distinguishing statements from questions, and also distinguishing the emotion of the utterance. For example, this one.
309.
What kind of emotion do you feel the person is expressing? Surprise? Exciting? Okay. So it's kind of a more positive emotion, right? It's not sad or not depressed. And also when we listen to music, we're able to detect the pitch, detect the melody, we can infer the scale. Okay, so Western style. And this one uses a totally different scale. And the third one. The third one is from Japan. Their scale, traditional Japanese music scale, is very different from other parts of the world. Okay, so here is a general process for pitch detection, right? Because pitch within audio changes over time, all the time. So we have to segment the audio into short segments before we're doing pitch analysis. So the first step is segment into time frames. And then for each frame, we're going to try to detect pitch, if any, right? And then in the third step, we do post-processing to consider the contextual information about pitch transition from one frame to the next. Okay, so here's an example of speech utterance and the pitch contour. We take the waveform and we can use different pitch detection methods, for example, in Pratt or Ispana. And we can also plot the ground truth. We can see that for many of the frames, the pitch detection results of the algorithms align with the ground truth very well. In some frames, they are different, right? Some methods says there's pitch, some methods says there's no pitch. And when they say there's pitch, their value report is different too. So let's go through the steps briefly. The first step is to segment the audio into short frames. but we can't make the frame too long or too short. If it's too long, then the pitch might have changed. We're only trying to estimate a single pitch value from one segment, one frame. So the frame cannot be too long, right? But if it's too short, we do not have very reliable detection of the pitch because of the time frequency resolution trade-off. And in the time domain, we need to have at least 3 periods of the signal to detect the period reliably. Okay, that's a rule of thumb. But if we go to the frequency domain, then we will have this time frequency resolution trade-off. If the frame size is too small, then the frequency resolution will be very poor. We cannot distinguish sinusoidal peaks if they are close to each other. They will merge into a single peak. Then how can you detect the harmonics and detect the pitch? So, but when we design the frame length, we also need to think about what kind of audio we're dealing with. For speech, the pitch changes relatively faster because the pitch, the vowels are connected to each other and they always change. For music, at least for Western music, within each note, the pitch is relatively stable, even though there's vibrato, but that's just small fluctuations. So depending on the data we're dealing with, we can choose different window lengths. Typically for speech, we can choose a length between 20 milliseconds to 40 milliseconds, something like that. For music, we can choose a window length between 40 milliseconds to maybe 60 milliseconds, something like that, around 50. And also because music has a wider pitch range, right? The lowest pitch can be as low as 27 hertz on the piano. For speech, it can only go as low as about 50, 70 hertz for low male voice. So when you have a very low pitch, in the material, in the audio recording, then we would have to use a longer window because otherwise we don't have enough length to cover 3 periods of the waveform. Even using a 60 millisecond window, we cannot cover 3 periods of the lowest note of piano, but we have to deal with that. So that's the primary reason why pitch detection for very low notes of the piano would not work very reliably, because it's because the length of the frame is not long enough. Okay, so let's discuss how can we design pitch detection methods, right? As we know, pitch is related to the period of time domain signal. It's also related to the greatest common divisor of the harmonic frequencies in the spectrum. It's also related to the common space between adjacent harmonics in the spectrum, right? So we can consider how to detect those 3 quantities from the signal or its transforms. Now, first, in the time domain, we try to detect the period because we know fundamental frequency is 1 over the period. Taking the time waveform, if we're able to detect the period, then we are good. We can find out the pitch. Okay. Now, if we go to the spectral domain, if we are able to detect or calculate the greatest common divisor, then we know the pitch, right? We know the fundamental frequency. Or we can detect, if we can detect the gap between adjacent peaks, we can get the pitch, right? So these are the 3 kind of cues or considerations for us to design pitch detection algorithms. And people have designed those algorithms using these cues. So in the time domain, we try to detect the period of the signal. In the frequency domain, we try to detect the divisor, common divisor of the harmonic frequencies. And we can go to the capsular domain to detect the gap between harmonics in the frequency domain, right? Because the gap is the period of the frequency domain signal. And how do we detect the period? Well, we can go to another Fourier domain, which would be the capsular domain. Okay. So let's briefly look at these methods. In the time domain, how to detect the period? Any technique you can think of to detect the period of a periodic signal in a time domain? Autocorrelation. Yes, autocorrelation. That's very effective and straightforward method, right? So we have the signal, it's periodic signal. We will shift it to different time lags, tau, and then multiply it with the original signal pointwise, and then sum all the multiplication together. That is autocorrelation. And we got a value. This value tells us the match between the original signal and the shifted signal for this amount of shift, tau. We will do this for all the tau values. And if the tau value equals to the period of the signal. Then the signal is, after shifting, it aligns with the original signal exactly, right? So we have a square here, we have squares here, then summation will be very large. If the tau value is just half of the period, then the shifted signal is opposite to the original signal. And we have the multiplication, we have a bunch of negative values. And we have a very low value for the autocorrelation. So this is the autocorrelation function. The horizontal axis is a lag or the tau, and the y value axis is this autocorrelation function value. You can see that when the shift is the period, say here about 150 samples, right? 150 about here, one period, we have a very high autocorrelation value. But if you shift by 2 periods, you also get very high autocorrelation value because it's also a repetition of itself, and 3 periods, or 0 shift at all. It's just multiplication to itself. That's also high value. But if you shift by half a period or other shifts, you get low autocorrelation value. So with this autocorrelation function, if you're able to detect this first non-zero lag but significant peak, then we uncover the period of the signal. So that's the idea. But the problem is that we often misdetect these peaks, and that will give us a lower octave error for the pitch estimation, right? Because the estimated period is twice of the true period. That means the estimated fundamental frequency would be half of the true fundamental frequency, and it's called a lower octave error. So we need to somehow suppress these values. Another issue is that very often the signal modulates its amplitude. For example, if the signal increases amplitude over time, you can see the more you shift to the right, the higher value it could have after the multiplication, right? So that gives us bias to the shift. That's not good. Okay. So people later proposed to use this difference function to replace the multiplication between the shifted and the original signal. Actually, if you expand this this polynomial, you will have the square terms and also the cross term. The cross term is exactly the autocorrelation term we have seen before. But thanks to the square terms, now when the amplitude of the signal increases, the difference may the difference may not increase that much. Okay, I need to justify my statement. Okay, this may not be very accurate, but yeah, we can discuss that. Sorry? Oh, just magnitude. Okay, I see. Yeah, here they use square. Yeah. Okay. Yeah, I'm just presenting this paper called IN. And in this case, they're looking at difference. So they want to find the smallest difference over different taus. And that's why they call it IN. Yin and yang are the, in Chinese culture, yin represents the moon, and yang represents the sun. So that's, yeah. Or this is the mountain, this is the valley, something. Yeah, so basically they try to find detect the lowest depth, but it's the first occurrence of the lowest depth, and that will give us the estimate of the period. They have several other steps to make sure that we do not misdetect these peaks, these values, and but we'll skip those. We'll just present the key idea of the method. So there are also methods to detect pitch in the frequency domain. Right, as I mentioned, in frequency domain, we try to discover the greatest common divisor of those harmonic frequencies. Now, one approach is to calculate this so-called harmonic product spectrum, HPS. This is a very old technique, right? 1970s, 60s. But at then, computers are not that advanced, so they try to make the computation easily in those early devices. So what they do is they get the spectrum and then they scale the spectrum by integer ratios. Say this is scaling by 1/2, this is by 1/3, so that the third harmonic in this case would align with the fundamental frequency in the original case. And then they multiply all these different scaled versions together in pointwise fashion. Then they get this so-called product spectrum. And the product spectrum will show a high value at its fundamental frequency because it receives support from all its harmonics in the scaled versions. That's a basic idea. But there are many other methods in the frequency domain. The basic idea is still to receive some kind of support, right? For any pitch hypothesis, you want to receive as much support as possible from harmonics. Okay, and whichever hypothesis receives the highest support, then you say, okay, that's my pitch estimate. So that's the idea. You can define probabilistic functions to define the support. You can also just sum the energy at your pitch hypothesis, fundamental frequency hypothesis, harmonic positions, and so on. There are different techniques, but the ideas are very similar. And the third approach is going to the capsule domain. So we're trying to detect the gap between adjacent harmonic peaks in the spectrum. Now, if we look at the log amplitude spectrum, it's pretty periodic. It's an impulse repeated many times with a period. The period would be the gap frequency. So one way to detect this gap frequency is to go to the Fourier domain. To take another Fourier transform of this, right? We go to the so-called capsule domain. And in there, we can find the fundamental. So we use Fourier transform, and then we can go to the capsule domain. So this is the time domain signal. We can see it's periodic. And the period is roughly, I don't know, this is 0.01 second, right? If we look at the spectrum of the signal, we can see the fundamental frequency is roughly here, 100 Hertz. If we go to the capsule domain, we will see a strong peak. This corresponds to the period of this spectral signal. The period in a sense of Hertz. So you can see this corresponds to 0.009 second, which is basically the period in the time domain, and it is 1 over the fundamental frequency in the spectral domain. But we will also see some harmonic peaks in the capsule. For example, this is twice of this fundamental. We'll see the third and so on. If the analysis is here we truncate, you can have longer capsule. And thanks to the source filter model, right, we described that the capsule coefficient, the low coefficients, will represent the spectral envelope, the general envelope of it. And the high coefficients will contain the excitation signal information, which contains the pitch information and the harmonic information.
Second piece to be negative, but I think I will be later. The second piece that is coming here.
Yeah.
It should have negative. That is positive. The second negative, the third is positive. So after the longest pitch function of that function. Magnitude. Yeah.
Yeah, magnitude. That's right. Yes, it's a log dB.
No, per magnitude.
Sorry?
Yeah.
Yeah, the third one, the amplitude. Yeah, it's amplitude.
So magnitude.
Yeah, we don't, yeah, this is linear. So this is not displaying the decibels. If it's in decibels, yeah, they will more equal. So yeah, going to the capsule domain, we just detect the first strongest peak or the fundamental here. And then this tells us the period of the waveform signal. Yeah, so these are the 3 categories of methods for single pitch detection. There are many more advanced techniques following those basic ideas. Now, another task is to detect whether there's pitch or not in a frame. So some frames may be silent or inharmonic. For example, in speech, there are a lot of consonants, fricatives. They do not have pitch. For silence, we can detect it by computing the RMS value and setting a threshold. But how about inharmonic frames, right? They have substantial energy. It's just that their waveform is not that periodic, and their spectrum does not show very clear harmonic structures. Now, so these methods also need to come up with a method to tell whether they should report a pitch or not. For in, they set a threshold on the dip of that difference function. It's called aperiodicity. For HPS, they set a threshold on the peak amplitude of the product spectrum. And for Capstrom, they set a threshold on the ratio between the amplitudes of the two highest capsule peaks. And how to decide these thresholds? Well, it's still empirical, right? They hold some validation set and try different thresholds and see which one performs the best. That's how they pick it. Okay, so how do we evaluate pitch detection results? Right, first of all, we need to choose some materials, recordings. We can take a speech or music or whatever sound signals. And then we need to get ground truth. We need to have humans to annotate the pitch. Then we can compute the pitch and non-pitch classification error for every frame, right? And for pitched frames, we can calculate the difference between the estimated pitch and the ground truth pitch. And we can use thresholds to decide whether the estimated pitch is correct or wrong. For different recordings, for different type of recordings, we can use different thresholds. For speech pitch detection, people typically use 10% or 20% in hertz as a threshold. If your estimated pitch is within 10% of the ground truth pitch, then it's considered correct. But for music, the threshold has to be smaller because, 6% is the difference between C and C sharp. That means 3% is the middle point, the boundary, right? So if the estimated pitch is within 3%, we can still safely say that, okay, the pitch estimate is correct if it's mapped to the piano, the keyboard. If it's beyond 3%, then it's mapped to the next semitone. Right? So people use this 3% or 1/4 tone as a threshold in music, for Western music. If you want to analyze the macrotonal properties of the signal, you have to use even finer thresholds. So this figure shows, again, the waveform and the transcription results using different pitch detection methods. And you can see frame 25, there's no agreement among these three methods. For frame 65, there's somewhat better agreement. And when you look at spectrogram of the signal, you can see this 25 corresponds to some kind of non-pitched region, even silence region. And 65 is roughly here. So you see strong harmonics, although the pitch is changing very quickly. So the estimate may have some ambiguity, right? Okay, so that's single pitch detection in clean environments. The signal has no noise and we can find the patterns. But in practice, the signal is often present with noise. For example, we hear this. Can you hum the violin tune back? Yeah, that's great. So we are able to do that, right? Even though the noise is so strong. I think it's 0 dB between the signal and the noise. But if we were using the previous methods, the waveform is not periodic anymore. The spectral content will show very high noise peaks, and it's difficult to detect the harmonics of the pitch. And the capture method will fail as well. So how do we design algorithms to work robustly in noisy environments is a research problem. We can think about which domain is less sensitive to which kind of noise. Maybe some noise only are primarily present in the low frequency domain. Then maybe we go to the frequency domain and then focus our attention to the high frequency range to do the pitch detection, right? Or maybe some noise occurs sparsely in time, but whenever it occurs, it's very strong. In that case, maybe we just remove those time segments do analysis at other times. So we have to understand our signal before we can design a good algorithm. But to make it even more robust, we can take a data-driven approach or machine learning approach. We gather some annotated data and then train a machine learning model. So this is a supervised learning method. The model can be any model, say a SVM or probabilistic model or neural network. In this case, it's a neural network. And the model takes input, audio frames as input, and the output will be the target pitch. Right? During training, we feed the audio frames and try to output something close to the target pitch, and we compute the error between the output, the prediction, and the target pitch. And that's our error, and we compute the derivative of the error with respect to the model parameters so that we can optimize the model for the training data. So this method is data-driven, and it can be trained on any specific type of data. For example, you are trying to design a pitch detection algorithm for birds. Then it's better to collect some bird recording and annotations to train your method, right? It must work better than a handcrafted algorithm or than another model trained on human speech, right? But the model can also be trained on diverse data so that it can work on with diverse kind of data. So the model size can be big, can be small. It's very flexible using data-driven approach. And this method is called PRE. It's one of the state-of-the-art pitch detection methods. It's robust noise. So it's a convolutional neural network. It takes the raw waveform as an input, and then take the 1D convolution, several layers. And then finally, we have the fully connected layer to output the pitch range from C1 to B7 with pretty fine resolution. Okay. And the training will just be a classification problem. So you have input, then you classify, you choose the best among these 360 possibilities, right? And you train. So in the paper, they compare with existing methods. They compare with PIN. PIN is a probabilistic version of the IN algorithm, which is based on the time domain autocorrelation or difference function that we described. And SWAP is another state-of-the-art method. And you can see that for different noise conditions and different SNRs, right? 0 means stronger noise. You can see the creep method, the blue line, degrades less than the other two methods. So it's more robust to noise. Well, except for the brown noise. I don't know why. But you can find the online repo and model from this link. And the online model is trained on diverse data sets, music data sets. You can also augment your data with added noise so that it's more robust to noise. But now the limitation of this kind of supervised learning method is that it requires data with annotation. And we know annotation is time consuming and requires expertise in many cases. So in recent years, there has been some ideas on using self-supervised learning to address pitch detection problems. One method is called SPICE. SPICE stands for self-supervised pitch estimation. So its inspiration is this, most of us have relative pitch, right? We can sing a melody or hum a melody pretty accurately, but we don't know which hertz, which note is correspond to piano. That means we have relative pitch. We're able to recognize the relative intervals of pitches, but we are not able to map a pitch to its absolute value of hertz. There are some people who have absolute pitch. Kids who start learning music before, say, 5 years old, consistently, then they are likely to develop absolute pitch. Whenever they hear a harmonic sound, they can directly map to a piano. They know that's C, that's A, right? That's whatever hertz. But most of us only have relative pitch. Once we use relative pitch to transcribe the melody, and then we compare it with a reference tone, then we can figure out absolute pitch. Okay. So this method utilizes that idea. It tries to build a model that first recognizes the relative pitch, and then it goes to another calibration stage to calibrate the transcription to the reference pitch so that we can figure out, what are the other pitches, the absolute hertz on. Okay. Now, this is the model architecture. It takes unlabeled audio recordings, so just audio waveform, and then transform them into constant Q spectrograms. And they create transposed version for each of the recording. This is the original recording. It feeds to here, but it also creates a transposed version feeds to this branch. And we know the transposition amount, which is K2 minus K1. We know how much we transpose it. Okay. Then both of them will be passed through some encoder to output a pitch value. This outputs a pitch value. We don't know what exactly the absolute value is, but we know the difference between these two pitch values. The two pitch values should be, the difference should be K2 minus K1, and that's the training target. Okay, so you compute the difference between these two and you define the loss. The loss will be the difference between K2 minus K1 and the difference between the two outputs. Okay, they also introduced two other losses. One is this confidence. So the confidence means whether there's a pitch or not in this setup. So whether this frame contains a pitch or not, whether this frame contains a pitch or not. Well, you can see that because they are the same time step, they are only differed by a pitch transposition. So if this branch says there's a pitch, then this branch should better say there's a pitch too, right? There should be consistency. So they use this consistency to define this loss. Yes.
So we do log scale shifting it is scale.
Exactly. Yeah, so log scale shifting. So this is music transcription. Yeah, exactly as scaling, doubling or tripling rows. Yeah, scaling. And the third loss is a reconstruction loss. So they have a decoder to decode the signal or spectrogram back from the estimated pitch values. So they use the three losses together, but the primary losses is the relative pitch loss and this consistency on the confidence scores. That's a self-supervised learning technique, right? So now you can take whatever recording as long as they are harmonic, right? You take them and you feed it to the model to train. You don't need any annotation, just train. After training, the model is able to recognize the relatives of pitches. Once you have that, you take the encoder to, you have your test material to transcribe. You feed it to the encoder to output some pitch value, right? Then you can calibrate that value on a small portion of your data to the absolute pitch. After the calibration, then all the other values will be moved to their corresponding values. So you achieve pitch detection. Okay. So they compare with the.
So
Yes.
why are they using reconstruction loss?
Yeah, so I'm not exactly sure. I think they want to make sure this pitch output is not trivial. Okay. But that's a good question, Yeah. So this is a comparison with creep. We can see the model parameter can be much smaller than the creep model. And the creep model, or supervised model, is trained on many different data sets. And the SPICE-SPIR is only trained on single voices. And this is a raw pitch accuracy. And we can see the accuracy is comparable between the self-supervised learning and the supervised learning. And here they have other comparisons. Let's see here. Oh, this is a noisy condition, right? 20 dB SNR, 10 dB, 0 dB. So in 0 dB, you can see SPICE works better than the full model. The full model has 22 million parameters. SPICE has 2 million parameters. So this method has a smaller model. It has decent performance and it's better in noise, better noise robustness. That's the power of self-supervised learning. And this year, there's another self-supervised learning method called PESTLE. This is the best paper of ISMIR this year. And this stands for pitch estimation with self-supervised transposition equivalent objective. So nowadays, in order to publish, you have to come up with a nice abbreviation of the title. So all these methods have some kind of interesting names. And the idea of this method is, again, to transform the data into different versions and draw relations between those versions. So in this case, we are looking at a constant Q spectrum of a frame of the audio. And we have the original version X. We have a noisy version X cubed, so we just add some noise to it. And we have a shifted version, pitch shift, left and right shift, right? XK, and also noisy pitch shifted version, X cubed K. Okay, now we can construct, look at the relationships. So we pass these three things, the original, the noisy, and the shifted noisy, to the same neural network, X theta, and compute the probability of the output. So this is the pitch range. And we want these two outputs to be close as possible, right? Because this one is the original, this one is the noisy version. We want the model to be noise robust. So we want the output between these two to be very similar. So this is called invariance loss. We want the pitch detection result invariant to the noise. Okay. Now, between the noisy version F theta and this noisy and shifted version, this one, we want equivariance. So the difference between these two is the shift of pitch. Equivariance means that so basically equivariance is one kind of invariance, but it's, okay, how do I explain it? For example, we have a object detection problem in image, right? You have a dog in the image. Now you're trying to recognize what animal this picture contains. Okay, if the dog is in the center of the image, you say it's a dog. Oh, sorry, not on. Okay, what should I say? Maybe that's invariance. So equivariance means you're trying to detect the position of the dog. Okay, if the dog is at the center of the image, you say, okay, it's at the center of the image. Now, if you shift the dog to the left side of the image, okay, then your output should also be shifted. So the output should be shifted at the same amount as your input. That's called equivariance. It's equivariance to translation. And the same concept here. Your input is shifted along the pitch scale, then your output should also be shifted along the pitch scale. That's equivariance. They also compute this so-called shifted cross entropy. So it's also capturing this equivariance, basically. So now with this, they train the model and they are able to get very good results. You can see Pascal has very good result on its ISMIR 1K dataset, which is 1,000 pop singing, Chinese songs. Comparable to the CRIP model. But remember, a CRIP model is supervised, and this model parameter is 22 million. This model is 28K, so 1,000 times smaller. And that's the main reason why this method received the best paper. It's so efficient and elegant. So this is an extremely light model. It's comparable, achieving comparable results with supervised methods. All right. Any brief questions? Yeah, I should move faster. Okay, then let's move on to multi-pitch analysis. So previously it was single pitch, but in many music mixtures, we have multiple pitches at the same time. How do we detect the pitches? Actually, we gave a tutorial in 2015, and it contains much more content than today's talk. And yeah, you're welcome to visit the link. So multi-pitch analysis is basically trying to detect the pitch values in every audio frame across a piece of music. So, and we also want to tell which instrument or which source produces that pitch. So we use different colors in output. Right? So our goal is to get this output from this input. And it's a fundamental problem in computer audition and also for ISMIR. It has many applications like music transcription, harmonic source separation, melody-based music search, chord recognition, music education. After you can transcribe the pitch, you can provide feedback to students. But it's a very difficult problem. So let's take a try. So here I'm going to play two chords. Each chord contains several notes. I will ask you two questions. How many pitches are there in each chord? And what are the pitches? If you don't have absolute pitch, you can just hum, right? I don't have absolute pitch either. So let's listen to it. How many pitches? 2 pitches, 4 pitches, 3 pitches. Okay, what pitches are they? Let's listen to it again. Okay, good. Now the second one. How many pitches? 3 pitches. Nice. What are the pitches? Okay. Yeah. Yeah. Let's look at the result. Oh, it's already shown. Oh, I'm sorry. I wanted to trick you. But anyway, so this has 2 pitches, C4 and G4, the 3 pitches, C, F, and A. But the killer question here is, can you find a pitch in the first chord and a pitch in the second chord that are played by the same instrument? This is a stream segregation problem, right? Or sequential grouping in auditory scene analysis. Let's listen to them again. Right. It's very hard. So the C4 are played by horn, and actually this G4 is played by clarinet, and this A4 in the second chord is also played by clarinet. Okay, so you can see that's the difficulty. So we need to, when we design algorithms, we need to first tell how many pitches are there in a frame. We need to detect the pitch values of those in frame, and also we need to consider different frames and try to stream the pitches into several voices or several sources. So these are the questions we need to answer. Okay, so this is our task. Starting from the waveform or from the spectrogram, we're trying to get output like the colored dots representing the pitch estimate at different time frames. And we can address this problem at 3 levels. Okay, the first level is just the frame level estimation of pitches and the number of pitches, which is called polyphony. And this is called multi-pitch estimation. There are many methods to do that. And the second level is to also estimate the onset and offset of a note in addition to the pitch. So in this case, we would have to string the pitch estimates across frames into notes. So we start to form some kind of structure. Right? This is called note level transcription or note tracking. And in the third level, we need to stream those pitches according to the sources across notes. So you can see that if you look at the pitch contour of a voice, it's not continuous. When you move from one note to the next, the pitch often jumps in Western music. So how do we stream them together? This is called stream level transcription or multi-pitch streaming or timbre tracking. We need to use timbre features to do this. Okay. So, yeah. Any questions about the problem setup? I always think that problem setup is more important than the techniques.
So when you're saying that only pitches and polyphony is the main part of the frame language.
Yes.
It also will automatically give us sets of notes, right? Because the new pitch is coming out. I didn't get the difference between note level and frame.
Okay, the frame level is detecting the pitches in each single frame. We do not have any connection across frames. But note level, we need to recognize notes. To form a note, note has the pitch, a sequence of pitches in different frames, but we also need to know the onset time of the note, the offset time of the note. Basically, the pitches across frames need to be stringed together into a note.
Oh.
Does that make sense? Yeah. Okay. Cool. Okay, so let's very briefly introduce some of the methods. So in the first level, we're trying to detect the pitches and the number of pitches, there's a classical method called iterative spatial subtraction. It's similar to iterative spatial subtraction for speech enhancement, for example. It's a similar idea. So it's an iterative process. We start with the signal for analysis. In each iteration, we try to only estimate one pitch. It's called the predominant pitch, the pitch that is most prominent in the mixture. We estimate it, and then we also estimate its harmonic envelope somehow. And then we remove the pitch and its harmonics from the mixture to subtract it from the spectrum. And then we check whether the leftover spectrum contains enough other pitches or not. If yes, we go to the next iteration to estimate the next predominant pitch, and then do the subtraction again and again, until we think, oh, the leftover is too sparse, there's nothing left, then we stop. Okay, so the idea is very straightforward, right? But the key challenge is to decide how much to subtract. We know that the simultaneous nodes, they share many harmonics. If you subtract too much, then you hurt the leftover nodes. If you do not subtract enough, then you have some leakage from the previous node estimate, right? So how do you decide how much to subtract is the issue. For example, this mixture spectrum, if we first estimate the lower pitch, we want to subtract this amount, right? But how do we decide this amount in practice? It's not easy. Okay, I will skip these methods, but there are many other methods. For example, we can go to the spectrum domain and design probabilistic models, say maximum likelihood methods, to tell which pitch hypothesis or which set of pitch hypotheses receive the highest likelihood from data. Okay, maybe I'll briefly introduce this one. So this is a spectrogram decomposition method. It's a probabilistic latent component analysis idea. Now we have a piano passage. And if we look at the magnitude spectrogram, we can see the harmonics of the notes. Okay, in this case, it's a monophonic piece, right? At each time, there's only a single note, but it's a good illustration for the technique. Now we take this magnitude spectrogram as a matrix. It's a non-negative matrix. All the values are non-negative. And then we can decompose it into these two non-negative matrices. Or in probabilistic language, we can decompose the distribution of the sound energy across frequencies at each time into this, into a so-called template distribution of the energy across frequency for the Z template, for the Z component. And then this is the prior probability of the Z component. So this PF given Z will have multiple Z's, and they are the columns of this so-called dictionary matrix. They give us the prototypical spectrum corresponding to different notes. So this one corresponds to the lowest pitch in this passage. This one is another pitch. This one is another pitch. And this PT of Z will give us this matrix, and each row will give us the activation of a component over time. So the first row will be PT of 1, the first component, PT of Z equals to 1 over time. And we see that it corresponds to this note, this pitch. It's activated at this time, and then activated again later time. Okay. For this passage, there are 5 notes, but there are only 4 unique notes. So here we only use 4 templates in the dictionary. Is the main idea clear? You can view it as a clustering problem. So you view it as a bunch of frames, and certain frames are very similar to each other. For example, this frame and the next frame, their spectrum are very similar to each other. And this frame, this frame and the last nodes, some frames, they are also similar to each other. After clustering, each cluster will be represented using a single representative spectrum, and that's the dictionary. And the activation tells us when that element is activated over time. Okay. Okay, so we can use the same technique to decompose polyphonic music spectrograms. But we can do this in unsupervised way. We can also do that in supervised way. For example, if we try to transcribe a piano, okay, we can first record the templates for every key of the piano. No, we can just press a key, we get a recording, we got a representative spectrum, and we use it as an element for the dictionary. And then when you have a piano passage to transcribe, you use the dictionary you pre-computed, and then fix it, and then just compute the activation of the different pitches across time. That is pitch estimation or transcription. Okay. I think we need to move quicker. So, but another method, totally different method, is classification-based piano transcription. So in this case, we view the pitch detection method problem as a classification problem. We try to classify whether a pitch is present or not in each frame. Okay. And we only consider those quantized pitches, 88 different pitches. This idea was first proposed using SVM classifiers back in 2007. And recently, in 2018, this idea was proposed again using deep neural networks. This is the onsets and frames paper from Google. Basically, they take the log mel spectrogram of the piano as input, and then they have two bidirectional long-short-term memory networks, and also some convolutional stacks here. One is predicting the frame level pitch activation. The other one is trying to predict the onset, whether the frame contains the onset of the note or not. So, and then this achieves the state-of-the-art piano transcription accuracy back then. And nowadays, almost all piano transcription methods are built on this kind of idea. So using deep learning and classification-based methods to do piano transcription. But this method cannot work with other instruments because this classification can only work with quantized pitch. For other methods like strings, there's vibrato, we want to detect the pitch fluctuation over time. If you discretize the pitch into very fine resolution, then there are too many classes. And also it's very difficult to obtain annotated data to train such models. For piano, it's easy because there are automatic pianos. You can drive the piano using MIDI files, and then you can render the acoustic recording. So you get the audio recording and the MIDI annotation of the pitch. You can have a large amount of that to train a model. But for general string instruments, wind instruments, it's difficult to get such data. One way to get the data is to align musical scores with musical recordings online. There are tons of music recordings, right? And there are tons of scores as well. So we could align the audio with a score using dynamic time warping. And the alignment may not be very accurate, but it may be good enough to provide supervision information to train models. And this is what this work is doing. In 2017, they collected 330 classical pieces from YouTube, I believe. And then they got a MIDI score to do the alignment. And then they are able to train a network based on the aligned score as the ground truth. Okay. So now they can work with multi instruments. Okay. I think I'll just briefly talk about maybe another 5 minutes, should be less than 5 minutes, to talk about the third level, stream level multi-pitch streaming. So in this case, we're not only trying to estimate the notes or the pitches in each frame, but we're also trying to connect the pitch estimates over time, over a long period of time, to form streams or sources. Oh, actually, I haven't talked about the second level, right? But I will just briefly mention it. So for the second level, we try to estimate, detect the notes. So one way is to move from the frame level to the note level. In the frame level, we have the frame level estimates. We can do thresholding and filling some holes or do some pruning to remove some outliers to form the notes. Or we can do median filtering at different frequencies to get reliable readings of the notes. We can also use HMMs to model the on and off state transition for each frequency to read the notes. There are many methods. There are also probabilistic methods, but I will skip that. Okay, so for the third level, we talk about the pitch streaming. Again, there are many methods. We can use supervised methods. If you know what instruments will be there in the mixture you want to transcribe, you can first collect some training data for the different instruments and train an instrument model or timer model. And then during transcription, you can apply those timer models and trying to estimate the pitch of that instrument in the mixture. Okay. You can do this in a classification way. You can also do regression detection. Okay, but this is a supervised model. It cannot work with new mixtures or mixtures with new instruments that you have not collected training data for. You can also try to adapt your timer model to some unseen timers, but yeah, that's not easy. Another way is to view it as a clustering or unsupervised learning problem. So when we listen to a music mixture, we may have not heard those instruments before, but in the mixture, we can recognize the differences between timbre between the different voices. We can use clustering to cluster those pitch estimates in different times together into the sources of streams, and that can achieve the streaming. Right? So that's a basic idea. So I think I will just skip this. So yeah, we proposed this method several years ago on viewing it as a constraint clustering problem, and we tracked it. So this is actually Vipu's method, right? Also timer tracking, unsupervised model, also constraint clustering, but they use hidden Markov learning field as a clustering algorithm. Okay, I'll just skip this. This is too much. I just want to introduce this very recent development from Google. They are, you know, they have a lot of computational resources and they can train large, say, transformer models. This one, MT3, is multitask, multi-track music transcription model. Basically, they collect a lot of data sets from different instruments, you know, guitars or MusicNet has various orchestra instruments. This is synthetic sounds, and this is URMP, our recording in our lab, covering different instruments. They have different instrument combinations, different polyphony, okay, different pitch ranges, but they try to train the same model, and the model will be able to transcribe the pitch content of different instruments. For example, this one contains 4 instruments. It will transcribe the pitch content for each of the instruments. So it achieves pitch estimation, note tracking, and also timbre tracking. How do they do that? Well, very straightforward. When they train a model, the input would just be the log mile spectrogram. That's it, of the audio recording. Their model output will be the MIDI-like tokens. So they have the MIDI files. They are not necessarily aligned with the audio. Okay, this is a MIDI file. They tokenize it into this text. Right, this is a time, you know, onset time of this first set of 2 notes. This belongs to this particular instrument, and this is a onset time. And note 22 is a pitch 22, and also note 24. They are on. And at time 0.63, these 2 notes will be off. Okay. And then you have another note on, but this is a different instrument, the yellow instrument here. It's note 29. So they convert MIDI files into these natural language tokens. And then they use transformers to map these 2 sequences. The log mile spectrogram is a log mile spectral sequence to the token sequence. That's it. They just train on these data sets. And then they achieve, they train the data. These are the data they use to train. Okay. The hours of audio, you can see, is quite large. And this is the result. They evaluate on different data sets, and they compare with some existing models. You can see they achieve pretty good, very much better results actually compared to previous methods. Okay, so yeah, that's brief. So briefly summarize. So today we talk about the basic concepts of pitch. We talk about pitch perception from first principles, what attributes are related to pitch, and the relation between pitch and music. We then take single pitch detection to go through how to design a pitch detection algorithm. And we also talk about machine learning based models. And eventually we reach to multi-pitch analysis. And we talk about 3 levels. And multi-pitch analysis is still active research area. I view it as the pearl of the crown of MR research. Yeah, that's it. I welcome you to join this research field. Yeah, it's very exciting. Thank you. Any brief questions? I think maybe, okay, yes.
A comment that the multi-pitch streaming approach seems to be as complex as building a LLM.
Yes, sort of. Yeah, although we didn't use training, we don't have any training. It's just clustering on the piece we work with.